This is the 21st example video to go along with our lecture videos on abstract algebra. And in this 21st lecture video, we looked at ring homomorphisms and isomorphisms, as well as the first isomorphism theorem of rings. And I'd like to start this video by stating and proving the second and third isomorphism theorem of rings before looking at some more examples. So the second ring isomorphism theorem says this. So let's let R be a ring with a subring S and an ideal I. Then the first thing that we'll prove is that S plus I, which is everything of the form little s plus little I, where little s comes from S and little I comes from I, is a subring of R. Next, we'll prove that S intersect I is an ideal of S. And finally, we'll prove the isomorphism, that S plus I mod I is isomorphic to S mod S intersect I. Okay, so let's get to it. So we'll start with this magenta dot and then just move down the line. Okay, so we'll use the subring test to prove this. So let's recall that the subring test says that all we need to do is show that this object is closed under subtraction and multiplication. So let's suppose that little a and little b are in S plus I. Okay, but notice that means that little a can be written as R plus, or maybe I'll call it S1 plus I1, and little b can be written as S2 plus I2. And this is where S1 and S2 are from S, and I1 and I2 come from that ideal I. Okay, great. And now let's look at both their difference and their product. So notice that A minus B, by like associativity and commutativity of addition, is equal to S1 minus S2 plus I1 minus I2. But now looking at this, this is pretty clearly something in I plus something in S. I guess I said those out of order, but that's okay. That's because I and S are both subrings themselves. So that makes this thing inside of S plus I, which is exactly what we need to have closure under subtraction. Now let's look at closure under multiplication. And I'd like to quickly point out that we've got an arbitrary ring here. This is not a commutative ring, so we do not have commutativity with multiplication necessarily. Okay, so this is going to be S1 plus I1 times S2 plus I2. And multiplying this out, we'll get S1 S2 plus S1 I2 plus, let's see, I1 S2 plus I1 I2. Okay, that's just keeping in mind all of the potential lack of commutativity. But now let's look at this. Because I is an ideal, we have an absorption property, both from the right and from the left. So that means all of these things are elements of I using the absorption property of the ideal. I guess along with this over here is two elements from the ideal, and the ideal is a subring. But that's kind of maybe even a special case of the absorption property, if you will. And then this S1 times S2, since S is a subring, this is inside of S because being a subring means you're closed under multiplication. So notice this is something in S plus something in I, so this is in S plus I. So that means we've proved this first dot, and let's move on to the second. Okay, so now let's look at this second dot, that S intersect I is an ideal of S. So in order to prove this, we first need to show that it's a subring, and then after showing it's a subring, we need to show that it has the absorption property. And then we're good to go. Okay, so let's show that it's a subring first. So let's suppose A and B are in S intersect I. And some people might say this is clearly a subring, but I think it's useful to go through all of the details now and then. So notice this tells us that A and B are in S and A and B are in I. Again, that's by the definition of intersection. But that means that A minus B is in S and A minus B is in I, because S and I are both subrings. Ideals are a special class of subrings. But then A times B is in S, and A times B is also in I. Again, because they're both subrings. But now putting these last lines together, that tells us that A minus B and A times B are in S intersect I. But that's where we needed to end up for this subring test. So yes, S intersect I is a subring. And here we didn't use the fact that I was an ideal. In fact, the intersection of any two subrings is a subring. Okay, so now let's prove the absorption property. So let's suppose that A comes from S intersect I, and maybe we'll say little s comes from S. And we want to show that AS is in S intersect I and SA is also in S intersect I. So let's see how to do this. So let's notice that we immediately know that A is in S and A is in I, just by the intersection. But since S is a subring, that tells us that SA and AS are in S. But since I is an ideal, the ideal I has the absorption property, so that means that SA and AS are in I, by absorption property of the ideal. But then we'll just bring this and down, and notice we can put those two things together to say that SA and AS are in S intersect I. This may look like just the multiplicative property of being a subring, but the important thing here is that while A comes from the intersection, this S is just anything in sort of the larger subring, if you will. Okay, so we've proven the second dot that S intersect I is an ideal. Now let's move on to the most important part, the isomorphism. Okay, so we'll finish the proof of this off by showing that S plus I mod I is isomorphic to S mod S intersect I. And we'll do this by constructing what I'll call an obvious homomorphism, and then showing that it is surjective and finding the kernel. Okay, so let's define the following map. So it'll be phi, and it goes from S plus I into S mod S intersect I. And what does it do? Well, notice that everything in S plus I is of the form little s plus I. And then everything over there is a coset built out of elements from S. So let's map this into the coset S plus S intersect I. And let's try to be a little bit more exaggerated with our capital and lowercase s's so it's not confusing. Okay, so that's our map. Okay, so notice that this is kind of like obviously surjective. That's because everything over here is of this form with a representative S, and we can attach this representative S to a number of different elements over here, depending on how big I is, and all of those get mapped to the appropriate coset. So I'll just put down here that it is surjective, really just by construction. Okay, so since it's surjective, all we need to do is find the kernel, and hopefully the kernel is the ideal I, which sets up the first isomorphism theorem to really give us this result for free. So let's suppose we have something in the kernel. So we've got S plus little I is in the kernel of phi. But notice that's equivalent to phi of little s plus I is equal to 0 plus S intersect I. That's what it means to be in the kernel. You're mapped to the 0 element. Okay, but now we can apply the rule for our map, and that gives us S plus, let's see, S intersect I is equal to 0 plus S intersect I. But those two cosets are equal if and only if S is an element of S intersect I. But now if S is an S intersect I, and let's recall up here, just by the shape of the domain, we know that S plus I is in S plus I, in other words, little I is in I, then putting these two things together, we'll see that S and I are both in I, which means that S plus I is in fact in I. Okay, but let's read this from the left-hand side to the right-hand side, and we've shown an equivalence between being in the kernel and being in the ideal. but that means that the kernel of phi is in fact equal to this ideal. But now we can apply the first isomorphism theorem of rings. Let's recall what that says, like just in general terms. It says that R mod the kernel of phi is isomorphic to the image of phi. So putting this all together, our ring is S plus I in this case. Mod the kernel is simply this ideal, is isomorphic to the image, but we showed that this thing, or we argued that this thing was surjective, so that gives us the appropriate right-hand side, and there we have it. Now let's look at the third isomorphism theorem. Now we'll move on to the third isomorphism theorem of rings. So let's say we have a ring R, and we have these nested ideals. I is inside of J, which is inside of R. Then we'll show that R mod I mod J mod I is isomorphic to R mod J. So this looks like we're taking the reciprocal and then canceling things out. But of course, that's not what we're doing. But that gives us motivation not only for our notation, but also for our naming convention as a quotient ring. And then for free inside of the proof of this, we'll show that J mod I is an ideal of R mod I. And that's just by exhibiting it as the kernel of a ring homomorphism. And the kernel of a ring homomorphism is always an ideal. I think we proved that before. Okay, so let's see how to do this. So we're going to start by defining an obvious map. So I'll take this phi and it'll go from R mod I to R mod J. So it comes from the numerator, if you will, over here to R mod J. And recall that everything in R mod I is a coset. So we need to determine where to send the coset R plus I. And the obvious place would be to the corresponding coset R plus J. And now anytime elements of your domain have different names, like their equivalence classes, you have to check that your function is in fact well defined. And we are in that setup because we're inside of a quotient ring, and things could have different names. There are coset representatives that could be different. Okay, so let's show that we are in fact well defined. So let's suppose that inside of R mod I, we have A plus I is equal to B plus I. Okay, but let's notice that that means that A minus B is an element of I. That's by coset equality theorem. But now I is a substructure of J. So this is inside of J, but now cutting out the middle, we have A minus B as an element of J. But now putting this back into terms of cosets, that means that A plus J is the same thing as B plus J. But now putting that in terms of our map, we see that phi of A plus I is in the end equal to phi of B plus I. But that shows that it's well defined. We took two members of the domain that had potentially different names. Well, I guess it was a single member of the domain that had potentially different names. And we showed that the value of the function on that element didn't depend on the name. Okay, so this is well defined. Now it's like kind of clearly an onto ring homomorphism, so we won't even worry about that. We'll just find the kernel and that'll finish it all off because we can apply the first isomorphism theorem again. Okay, great. So let's see how to do this. So let's suppose that R plus I is inside of the kernel of phi. So notice that's if and only if phi of R plus I is equal to 0 inside of R mod J. But 0 inside of there is the coset 0 plus J. But now let's apply the mapping rule for phi, which is defined right here. So that's R plus J is equal to 0 plus J. But now those cosets are equal if and only if R is an element of J. But if R is an element of J, then this coset is really inside of the quotient space R or J mod I, because we've got an element of J plus the ideal I. We've got a coset of that structure. But now, since these are all if and only if statements, we have now the kernel of phi is equal to j mod I. But that's exactly what we need, because now we can apply the fact that R mod the kernel is isomorphic to the image. Well, I guess it's not R in this case. Domain mod the kernel is isomorphic to image. So domain is R mod I here. Mod the kernel, which we just showed to be J mod I, is isomorphic to image, which is R mod J. And we've done it. Okay, let's move on to some other examples. For our next example, we'll find all ring isomorphisms from Q adjoin root 3 to itself. Okay, so let's first notice that phi of 1 must be equal to 1. And that's because in a ring isomorphism, the multiplicative identity has to be mapped to the multiplicative identity. You could just restrict this to the group of units and see that. Okay. So we know that phi of 1 must be mapped to 1. So now let's notice that if n is a natural number, then we have phi of n is the same thing as phi of 1 added to itself n times. But since we have a ring homomorphism, that's phi of 1 added to itself n times, but that's exactly equal to n, because each of those phi of 1s is equal to 1. So in other words, phi is the identity map, at least on the natural numbers. And then let's also notice that phi of 0 must be equal to 0. That's because the additive identity has to be mapped to itself inside of a ring homomorphism. But this is the same thing as phi of n plus negative n. But then that's the same thing as n plus phi of negative n. But that tells us that phi of negative n must be equal to negative n. So let's see where we are so far. So far, we have the following. We know that phi must map any integer. So let's maybe write the integer as m to itself. So this is true for all integers m. Okay, great. Now let's see what's happening with reciprocals of integers. So let's also notice that phi of 1 is the same thing as phi of 1 over n added to itself n times, which is the same thing as phi of 1 over n added to itself n times, where now I'm like using the fact that we have a ring homomorphism there. But we've just talked about how phi of 1 must be equal to 1, and then this over here is exactly equal to n times phi of 1 over n. So in the end, solving, we see that phi of 1 over n equals, let's see, 1 over n. So that's for reciprocals of natural numbers. I guess maybe we'll point that out here. This is for all n inside of n. Now let's notice for all rational numbers, this function also has to be the identity function. So let's suppose that m over n is an element of Q. But now let's look at phi of m over n, which is the same thing as phi of m times phi of 1 over n, because we have a ring homomorphism here. But by our previous parts, that's equal to m over n. So let's see where we are so far. So far we have the following. We have phi of x equals x for all x in rational numbers. But now we haven't done anything with the square root of 3. Let's try to figure out where the square root of 3 must be sent. So let's set phi of the square root of 3 equal to y. And now this is going to be some element of Q adjoin root 3. Okay. But now we can look at the following equation. So 3 is the same thing as phi of 3 by this previous calculation we've done. But that's the same thing as the phi of the square root of 3 times the square root of 3. But that's going to be the same thing as phi of the square root of 3 all squared. Okay, but now taking the square root, we actually have two possibilities here. That means that phi of the square root of 3 can be equal to plus or minus the square root of 3. Okay, now all together, we have the following. We have phi takes a plus b root 3, which is an arbitrary shape of an element inside of Q adjoin root 3, and it must send it to a plus minus b square root of 3, depending on the behavior of what happens with the square root of 3. All of the rational numbers have to be fixed though. And then from here, all you have to do is check that each of these is indeed an isomorphism, which is not super hard to do. So let's notice that we have exactly two isomorphisms, one attached to the plus and one attached to the minus. Okay, let's move on. Next up, we'll show that Q adjoin root 2 and Q adjoin root 3 are isomorphic as additive groups, but not as rings. And I'd like to point out that previously we proved that these were in fact fields, so we could also say they're not isomorphic as fields. Now, I'm not going to go through all of the details of the additive group isomorphism. I think this is like pretty clear. You would take the element a plus b root 2 and send it to the element a plus b root 3. And since all you're doing is addition here, well, there's not really much to it. This is in fact just like a linear transformation as looking at these as vector spaces. And now let's see what goes wrong if we try to say that there is an isomorphism at the level of fields. Okay, so let's work by way of contradiction as I just alluded to. So let's suppose we have an isomorphism, and that isomorphism, we'll call it phi, and it goes from Q adjoin root 2 to Q adjoin root 3. Great. And now from the last problem, actually from exactly the same calculation in the last problem, we know that phi of x must be equal to x for all rational numbers x. So that's not a hard calculation. Now let's see what might happen to the square root of 2 and see where things go wrong there. So notice we'll have 2 is the same thing as phi of 2 from this rule up here, but that's the same thing as phi of the square root of 2 quantity squared, but that in turn is the same thing as phi of the square root of 2 all squared. Okay, but now let's set phi of the square root of 2 equal to a plus b times the square root of 3. We know that it'll be of that form because it's inside of Q adjoin root 3. I guess the important thing here is that a and b are inside of Q. Okay, but now what do we know? Well, we know that phi of root 2 squares to 2, and then phi of root 2 must have this form. So that tells us that we have this equation, a plus b root 3 quantity squared is equal to 2. But now we'll see the contradiction come pretty quickly. Let's multiply this out. We'll have a squared plus 3b squared plus 2ab root 3 equals 2. And then moving some things around, we'll end with the following. We'll end with the square root of 3 is in fact a rational number. But that's a clear contradiction. We know the square root of 3 is not a rational number. You might say, well, how did we get there? Well, we can solve this equation right here for the square root of 3, and that's what we end up with. So let's see. We would have the square root of 3 is equal to 2 minus a squared minus 3b squared over 2ab, but that's a combination of rational numbers, so it is a rational number. You might say, well, what happens if a and or b is equal to 0? Well, notice that if either of those is equal to 0, this zeroes out, and that gives us maybe another case. So if a times b is equal to 0, then we have a squared plus 3b squared is equal to 2. But now there's a fairly easy number theory result that'll show that this is false. I'll let you guys look that up if you need to. So this also leads to a contradiction. So either way we have it, we have an impossibility of a field isomorphism between these two spaces. So for our last problem, we'll find all ring homomorphisms from Z30 to Z20. And we're going to do this in stages. So we'll first find all possible additive group homomorphisms and then impose the ring homomorphism structure. Okay, so let's point out that we're working with additive group homomorphisms first. Okay, so notice as additive groups, everything is going to be determined by where we send 1. In other words, the value of phi of 1. Okay, let's recall the following fact, which says the order of phi of g must divide the order of g. And this is true like for any homomorphism. Okay, so that means inside of here, we have the order of phi of 1 must divide the order of 1. But this order of 1 is occurring over here in Z30. So that tells us that the order of 1 is 30. So we know the order of phi of 1 must divide 30. That means that the order of phi of 1 must be a divisor of 30. So we have the order of phi of 1 comes from a fairly small set. 1, and then let's see the divisors of 30. So 2, 3, 5, 6, we have 10, we have 15, and that's it. But then also, since phi of 1 is in Z20, we know that the order of phi of 1 must divide the order of the group, but the order of the group is 20. Okay, so what does that tell us? That tells us that the order of phi of 1 must be a divisor of 20. So what possibilities does that give us? So we have 1, 2, 4, 5, and 10. And that's it. And now we just need to look at the overlap of these possibilities. So let's see. We do have some overlap. We have overlap at 1. We have an overlap at 2. And then we have an overlap at 5. So those are our possibilities. Okay, so let's write those out. So we know that the order of phi of 1 really comes from the set 1, 2, 1, 2, or 5. Now let's also impose one of the conditions of being a ring homomorphism before we finish this thing off. Okay, so to be a ring homomorphism, well, you have to be able to factor across the multiplication. So we know that phi of 1 must be equal to the same thing as phi of 1 squared, which is the same thing as phi of 1 quantity squared. So that means that phi of 1 must be something called an idempotent. Okay, so now we've got two conditions to play off of. We have the additive order, maybe I should be saying here the additive order of phi of 1, and the fact that phi of 1 must be an idempotent. And let's look through the cases at this point. So let's say our first case is the case when the additive order of phi of 1 is equal to 1. But there's only one thing that has an additive order of 1, and that is 0. So we have phi of 1 is equal to 0. But then, does 0 satisfy this rule? Yes, it does. 0 squared is equal to 0, so that's okay. So notice if phi of 1 is equal to 0, then by the fact that we're in a homomorphism, that means that phi of n is equal to 0 for all n inside of our domain, which is in this case Z30. Okay, so that gives us one of our homomorphisms, the so-called trivial homomorphism. Now let's move on to the second case. So case 2, which would be the case when the additive order was equal to 2. So let's see that. So order plus of phi of 1 is equal to 2. But now let's look over here. In Z20, there's only one thing of order 2, and that is the number 10. I guess I should say additive order 2. So that means phi of 1 is equal to 10. But now let's check, is 10 an idempotent inside of Z20? I think it's not. Let's notice that 10 squared is equal to 100, which is equal to 0 in Z20. So that means 10 squared is not equal to 10 in Z20. So that rules this out as a possibility. So this does not give us a ring homomorphism. It is a homomorphism of additive groups, but not a homomorphism of rings. Now let's move on to case 3. So case 3 will be the case when the additive order is equal to, let's see, 5. So we'll have the order plus of phi of 1 is equal to 5. Now we're inside of Z20 here, so there's going to be a couple more elements. So that means that phi of 1 could be equal to 4. So notice that 4 has additive order 5. It could be equal to 8. That also has additive order 5. It could also be 12 or 16. So now, how am I checking those? Well, let's recall how to do this order. So the order of m inside of Zn, so I'll say in Zn here, is equal to, let's recall, it was n over the GCD of m and n. So that's a rule that really comes back and haunts us, if you will, from time to time, how to calculate the order of things inside of Zn. So notice all of these satisfy that rule. The GCD of 4 with 20 is 4, 20 divided by 4 is 5, the GCD of 8 with 20 is 4, so on and so forth. Now we have to check which one of those are idempotents, if any. So notice that 4 squared is equal to 16, but that's not equal to 4 inside of Z20. Let's move on to 8 squared. So 8 squared is equal to 64, but 64 is equal to 4, which is not equal to 8 in Z20. Now let's move on to 12. So let's see, 12 squared is equal to 144, but 144 in Z20 is equal to 4, that's not equal to 12. And then finally, let's move on to 16. So let's see, 16 squared, I'm actually going to write that as negative 4 squared, because 16 is negative 4 inside of Z20, and that makes it a little bit easier. Oh, but that is equal to 16. So 16 is an idempotent. So from that calculation, we see that 4, 8, and 12 are impossible, but 16 is possible. And that gives us our ring homomorphism that sends n to 16 times n for all n in Z30. And there we have it. Those are our two possible ring homomorphisms. The trivial one, and then the one defined by this 16n. And that's a good place to stop.